Okay, so let us start. And the plan for today is to fundamentally review machine learning, because deep learning, as I said in the last lecture, is a subset of machine learning. So today what we will do is we will spend our 1.5 hours, whatever it is, right, to review, which most of you or many of you already know, which is basically the fundamentals of machine learning and loss function, optimization, and all of those things. And the idea is that from next lecture we will try to go to deep learning, perceptron, and all of those things. So deep learning content will not start today; it will start from next lecture. Today's lecture is mostly about machine learning, right? Okay. So what we are going to do today is review of machine learning. Very quickly, can one of you tell me what is machine learning? What do you understand by machine learning? I mean, all of you know, but can you try to define it? Allowing machine or developing algorithms that allows machines to learn from the world. It can learn from data, and that is how it mostly operates, but it might learn from other things also apart from data, like physics, right? So machine learning, very broadly in a crude manner, is a set of algorithms that allow machines to learn from the world in a very crude kind of manner, right? So this is basically set of algorithms that allow machines to learn from the world. Okay, and mostly this part is through data. Mostly it is through data. In this course, it will always be data. So for the purpose of this course, it is a set of algorithms that allow machines to learn from data. And naturally, machine learning became so popular or is so popular in today's time because data is available in abundance. So as I like to call it, you can think of data as the fuel of machine learning. Without data, there is no machine learning. We will not talk about data processing as such, but data processing, data engineering, data science is essential for actually making these algorithms work. This course is not about data science, we will not do that, but you should keep in mind that that is essential for machine learning algorithms to work, right? Now, remember last time we were discussing what are the different types of machine learning algorithms that are there, right? So we are talking about different types of machine learning algorithms. And I did specify that the machine learning algorithms that are available right now can be broadly classified into three types. The first one is supervised learning, second one is unsupervised learning, third one is reinforcement learning. Now keep in mind there is also this idea of semi-supervised learning, there is also this idea of self-supervised learning, but those I will not go into. So broadly these are the three categories: supervised, unsupervised, and reinforcement learning. Okay. So we have supervised learning. I'm going to call it SL because I'm lazy. I'll not write it again and again. Then there is unsupervised learning, which is USL, and then there is the reinforcement learning. And today we will go into little bit more details about this than what we did last time. Reinforcement learning, RH. Okay. So supervised learning, unsupervised learning, reinforcement learning, right? So if we look into supervised learning, what is supervised learning? Here we learn from labeled data, right? So this is supervised learning, is learning from labeled data. Whenever you learn from labeled data, that is your supervised learning, right? Learning from labeled data. Okay. Now, for this course, I am going to represent data as calligraphic D. Whenever I write calligraphic D, that is your data. Okay. I mean, I do it for all course, but anyways. So in supervised learning, this basically means that my data set will be of this form. Okay. So this is basically saying I have n data sets and each data set is like a pair. Okay. So this basically is saying that there are n data set, I goes from 1 to n, and each data set is coming in a pair of x and y. Now keep in mind that x need not be a scalar. X can be a vector, even y can be a vector, but at least for our discussion I am going to take x as a vector. So whenever I give that line at the bottom, that means it's a vector. Those who are from mechanics have done APL 104, they know these notations. For others, I am repeating that below x, if I give a line, that means x is a vector. Okay. And y can also be a vector, but for now, let's take y to be a scalar. So in supervised learning, you will work with this kind of data set. The data set will always look like this, right? Where this x, we call it input, or we will call it input feature. This y is my label. So label data, right? So that label is y. There is a n here, right? This represents the number of data I have. Data, right? And in the superscript, I in the bracket means the data index. So x superscript bracket 1 means the first data. X superscript 2 means the second data. Okay. So this is the notation we are going to mostly use. Sometime I might have used notation, but mostly I will be using, or we will be using this notation in this course, so that it is easy to follow and I don't have to explain the notation again and again. Okay. Okay, so now can someone tell me what is the objective in supervised learning? What do you think is the objective in supervised learning? For unseen x, we need to predict y. So the objective in supervised learning is to learn a mapping between my input feature x and output y, such that using this mapping, I am able, or we are able, to predict responses for a new x that I observe for which y is not known to me. The objective is prediction and not just learning. Okay. The objective is prediction and not just learning, right? So we want to learn, but we want to learn a model that can predict. Otherwise, that what will I do with by learning only, let's say, between xi and yi, where or what will I do by only learning xi and the corresponding yi? Because for xi I already know yi. The idea is I want to know y for new x. I want to know y for data where x is not known. I want to predict. So the idea is to predict, right? And as correctly said, the objective is to predict y for a new x. So the objective is to learn a mapping M which maps from x to y, and here x and y are the variables, okay, x to y, such that we can use it to predict y star for new data, for a new data point or new input is probably the correct term, new data x star. So the objective is prediction. That is the objective. Okay, we want to use these models to predict. So if I have to give an example, let me give an example, right? So let's see example of supervised learning. Okay, example of supervised learning. So remember last lecture I gave one example that in this classroom, if I measure the height and weight, and from there I want to learn a mapping from height and weight to gender. That can be one thing, right? I can also try to learn a mapping from, let's say, attendance to CGPA. That's also possible, right? I'm not saying they are already always correlated, but we can try to see if there is a correlation or not, right? And there can be other things also. I can also try to learn a mapping from, let's say, plan of a house, location where that house is, to the price of the house. If the floor area is more, the price would be more. If it is in a very posh area, the price would be more. And so there is a correlation, for example, in this case. In scientific domain, we can think of predicting or learning a mapping from, let's say, USG or MRI data, MRI scan, that's an image, to whether someone has a tumor or not. I can try to learn that mapping. In mechanics, I can think of learning a mapping from, let's say, the material property to the response, or loading to the response for a given system, obviously. So all of these are problems where you can imagine that these are examples of supervised learning, right? So broadly speaking, in supervised learning, you will have something like this, right? You will have x1, x2, xk, and then y. So what is x1, x2, xk? I said vectors, right? So if I open the vector, I'll get the first feature, second feature, kth feature. So that is x1 to xk. And I'm assuming here k is my number of input features, input variables, whatever you want to call it. And then y is my response, right? And you can imagine that in this case, my data points will look something like this: x11, x21, xk1, y1, x12, x22, xk2. And then let's say I have what, n data points, so x1n, x2n, xkn, yn. So in supervised learning setup, this is how my data set will look like. Now x1 need not be a single point. You can imagine that x1 is the image itself. X1 is a time series itself. So you can imagine, I mean, although I'm drawing or writing it as scalar kind of thing, it is giving a feel of a table kind of thing. But you should bear in mind that it need not be a table. Each of this can be an image. It can be high dimensional, and all of that thing is possible. Okay, but obviously this helps us build a mental picture of what we will look into in a supervised learning setup, right? Um, this is how it will look, right? And obviously, and then what I want to do is, let me draw that also, write that also. And now for a new data point x1 star, x2 star, xk star, what we are asking is what is this value. So this is the value we want to predict. So this is how it looks, right? This is what we want to predict. Clear? This would be very easy. Now, supervised learning can again be of two types. Okay, so supervised learning, let me use this. Yeah. So supervised learning can be of two types. What are the two types? Regression and classification. Okay, the two types are classification. I will write classification first. Classification and regression. Okay. Here, yes. Good. Yeah. So classification. Can you define what is classification? What is classification? Predicted output is discrete. Everyone agrees? Finite discrete. Everyone agrees? So is it possible that in classification I am predicting a finite discrete number, but that is different from what I have in the training data? So that means in classification we are trying to predict which class, and this number of class is finite, my training data or unknown output, unknown input x star belongs to. So when you are saying discrete, you are actually in your mind it is right, but be careful, right, what it can mean. So in classification, what we are trying to do, or what is the classification problem? This y, right, this y that you see, labels, these are discrete. That is the first thing, right? The labels are discrete. And then when you are trying to predict x star, you are trying to predict which class x star will belong to. And that set of classes are known to you a priori, and all of them are present most in your training data. Make sense? I'll repeat. Okay, I'll also write. So in classification, the classes that are available y, right, those are discrete. And during prediction time, okay, our objective is to find out which class x star belongs to, right? So it is discrete finite, obviously, because that my training data is finite. And during prediction, we are trying to find out my test point x star belongs to which of the classes, right? So that is, so classification so we work with label data. So, this is basically supervised learning. We work with label data, the where the labels are discrete and during prediction in sometime in machine learning, deep learning, I will also call it inference. Statistically speaking, inference and prediction different things, but for the sake of this course, which is mostly deterministic, we will be using inference and prediction interchangeably. Okay, so keep that in mind. But statistically speaking, if you look into dictionary and statistics, inference and prediction has a very different meaning. But in machine learning, deep learning, we have used this kind of terminology, and both are same. Okay, and during prediction, we want to predict which class a new input x star belongs to. Okay, I mean, the definition can be much more crisp, but I'm just trying to lay out everything that you should know. So in classification, the idea is that you have discrete classes and you want to know during prediction which class a new point belongs to. Can you give me an example of classification? Louder. Dog versus cat. So what is the input? Images, right? And the output is dog versus cat. It is classification because for a new image, you are trying to find out it is dog or cat. It will not work if you say the new image is of a lion, right? The example that I gave, gender, that is also a classification, male, female, right? That is also a classification problem. Okay, classification can also be like binary and multi-class, but that we will not go into right now. I think many of you know that it depends on how many classes I have. Am I only working with 2 classes, or am I working with greater than equal to 2 classes? So that makes it binary versus multi-class classification. Okay. Okay. So next is regression. Define regression. What will happen in regression? Now this y will be continuous. And what you are predicting, that y might not even be in the training set. It might be some new y. So in regression, it's basically continuous level. Regression is about continuous level. Okay. So the levels are continuous, and while predicting, it can be something new that never appeared in your training data earlier. Okay. Okay. Can you give me some classification algorithms that you might be, or some of you might be aware of? SVM, decision tree, then logistic regression. Okay. And there are many other. Okay. So we'll write it later. Regression, some algorithms that you are aware of. Linear regression, support vector regression now, SVR, Gaussian process regression, and then there could be others also. Okay. Okay. So this is all for supervised learning. Okay. The next one is unsupervised learning now. Unsupervised learning. So what is unsupervised learning? We work with unlabeled data. There is no supervision, there is no label, right? So this is basically we work with unlabeled data. So in this case my data set will look like xi, sorry, xi I equal to 1 to n. Okay. You can see there is no y now. Y was my label. It was there in supervised learning, or rather it was there, that's why we call it supervised learning. In this case, there is no label, I just have data. And then what can I do with the data? Okay. If you are working with a data set that looks like this, that is your unsupervised learning. Okay. Unsupervised learning can also, be of different types. Okay. Unsupervised learning can also be of different types. So three prominent types. So types of unsupervised learning. So what are the different types? Two I told last lecture, or all three I told last lecture, but anyways. So what are the different types of unsupervised learning? Just like there was classification and regression in supervised learning. So like that in unsupervised learning, what are the different types? Clustering, distribution learning, and feature learning. Three things, right? So here there is clustering, then distribution learning, and the last one is feature extraction. Feature extraction, feature learning, reduce order model, reduce space learning, whatever. Let me call it feature extraction. Okay. So clustering. What do you try to do in clustering? You try to find that if there is a natural clusters that are forming in your data. So in clustering, identify, whatever the clustering, whatever the dictionary meaning is, that's the thing. Identify clusters in data. Okay. For example, suppose this is my x1, this is my x2. This is not x and y. These are both input data. Remember, this x can be a vector. X there is can be a vector, right? It is mostly a vector. So I am assuming that x is a two-dimensional vector because that is what I can draw. Okay, 3D also probably I can draw, but not more than that. Okay. And now there is this x1 and x2, and I am plotting the data that I have. Okay. And maybe that plotting is forming something like this. Okay. So in clustering, the idea is you want to identify that this is forming a cluster and maybe this is forming a cluster. Okay. C1, C2. Keep in mind that in practice, the clusters might not be so well defined. You will not know how many clusters are forming because you cannot see it. So number of how many clusters are there, that itself becomes a hyperparameter. I will define later what is a hyperparameter. So it need not be that well defined, but broadly speaking, in clustering, this is what you are trying to do. You have a data and you are trying to find out if there is some cluster that is forming in your data. Now, what each cluster mean? What does C1 physically mean? What C2 physically mean? The algorithm will not tell you. You can look into this cluster and then analyze, and maybe you can assign a meaning. The algorithm will not assign a meaning to the clusters. Okay. So you can form clusters, clusters will get formed. all good and well, but the clusters, what is the physical meaning and all of those things, you will not know. Okay. Example of clusters is height and weight, maybe. Height and weight, if I plot, maybe there will be two clusters that will be forming. Okay. There can be more clusters also. Then images of dog and cat, someone was saying, so if I took those and plot the pixel values or something, I mean, I cannot plot very high dimensional, but if I can, hopefully some clusters will form there, but from those you will not know which cluster is dog, which is cat, you will not know which cluster is what. Okay. Any algorithm of clustering you are aware of? K means the most popular one, the first thing we learn in clustering, right? Next one is distribution learning. Distribution learning. Here what you try to do? You try to learn the distribution, probability density function, PDF, from where the data is generated. So you are trying to learn the distribution of the data itself. Because remember, your data now is of this form, d is equal to xi, right? And each of these x can be high dimensional, can be low dimensional as well. And you are trying to learn that what distribution this is generated from. And why do you want to learn that? Because if you can learn that, you can now sample the distribution and generate new data. This is the whole idea of distribution learning. Okay. So here the idea is finding distribution of D. Okay. D is data. So in distribution learning, the idea is to learn the distribution of the data itself. And if you can learn that, you can sample that data, sample that distribution, and that will allow you to generate new data from the same distribution. Okay. Example, generative model, all generative models that you know, VAE, GAN, diffusion, flow matching, normalizing flow, any generative model is, falls into this category, unconditional one, right? In the lower level, before we go to generative model, there is also this idea of mixture of Gaussian, right? Even a basic distribution fitting that many people do, not even doing machine learning, but they fit a Gaussian distribution, right? You have a data, you fit a Gaussian distribution, and maybe it fits. And if it fits, then you can sample from the Gaussian, and that will be your new data without actually going to the field and performing some experiments. So you can imagine, right? Let's say I have steel bars, right? I put it into a UTM and measure the elastic modulus of that steel bar. Okay, the Young's modulus. And then I have hundreds of such data. Now, if I know that it's a, remember when I do UTM to find out this thing, the bars are getting destroyed. So now if I know the distribution, I can generate data without actually destroying steel bar because that is costly. So I'm able to artificially generate new data without performing the actual experiments in the lab. That is why this is so powerful. Okay. So here the idea is to finding distribution of D. Example I already talked about, I'm not writing it, I'll write it at the end actually. And the last one is, I said, feature learning. Okay. Here you want to learn a low dimensional feature space. Given the data, you want to learn potentially a low dimensional feature space. Learning potentially low dimensional, it need not always be low dimensional, but feature space. Why we want to learn this low dimensional feature space? Because that is a very specific algorithm. In a generic sense, why will we want to learn to make sense out of the data often? Because suppose I have a data which is, I don't know, each data point is an image, it's a high dimensional image, thousands of pixels. Now we as a human cannot look into data and make sense out of it. Now if I can reduce that, I can potentially make sense out of that. That is one side. The other thing is that communication. Sending those huge data might take a lot of communication overhead, right? Because communication you are sending as bits or whatever. So if you can compress it and maybe send this compressed thing, which will then allow you to reconstruct at the source, at the destination. So from the source you compress it, send it like that, and then reconstruct. So that might also be an application. Computational cost obviously is an application. Low dimensional data is always easy to handle for the computer. So even computational cost is a reason for. Okay. An example, you were already saying PCA, principal component analysis, or for proper orthogonal decomposition, they are kind of identical. So that is one example. Autoencoder is another example. There is also this idea of GPLVM, Gaussian process latent variable model. So those latent variables are actually the hidden features. So that is also there. We will not cover GPL, any of this. We will not cover any of this in this course, but as an example, I am telling. So PCA, the most obvious one. Then the other one is autoencoder. It's a neural network based. And then obviously I said GPLVM, that is another example of this feature learning algorithm. Okay. So this is broadly speaking unsupervised learning. Okay. The third one is now, we'll move to that, reinforcement learning. Okay. So the last one is reinforcement learning. What is reinforcement learning? Here the agent learns from experience. In very short, that's what it is. So this is basically learning from experience. Okay. So here the idea is that there is a concept of what I call agent, not I call, everyone calls. So there is this concept of agent. The agent will perform action in an environment, and based on the action it will get a reward. I mean, positive reward is reward, negative reward is punishment. So it will get a reward. When I'm saying reward, remember it can be negative reward also. Okay. So it will get a reward. And then based on the reward, it will learn how to act in that environment. That is broadly the idea of reinforcement learning. Okay. So if I have to draw it, so here is my, let's say, agent. Okay. The agent in the environment will take an action. Because of the action, it will get some reward. And based on the reward, then the agent will, there is a feedback loop basically, and the agent will self-correct or learn how to act in the environment. Okay. So this is basically the feedback loop. Okay. So this is what, broadly speaking, reinforcement learning is. Obviously, and reinforcement learning generally is, when we will cover reinforcement learning to a certain degree, as I said, 3 lectures, 5 hours, something like that, and you will see that reinforcement learning is based on Markov decision process. There is the idea of MDP or Markov decision process, and this whole idea of reinforcement learning comes from there. Okay. Now there are some terminologies in reinforcement learning that I would like to discuss, because I think those are the very basic things of reinforcement learning. So the first one is environment. Okay. In reinforcement learning, you will often hear this term environment. Environment means the world. Okay. Okay. Then you will hear this term called agent. Now, broadly speaking, because it's a machine learning, right? So, agent is your machine. You can think of it like that. I mean, it was if it was not AI or machine learning, natural intelligence, then you are the agent in natural gas. So, it is the machine, broadly speaking. Then there is this notion of action. Action means performing a task, right, or performing something, right? That is action. So, and who performs? It is the agent that performs, right? So, it is the agent that takes action in the environment. Okay. Then there is this term reward that I already talked about. So, reward itself is self-explanatory. It's a prize that the agent gets, or it's a punishment that the agent gets, right? So, you can think of reward as prize versus punishment. Negative reward is punishment, positive reward is prize, gift, whatever you want. Reward itself means that. Okay, so these are the terminologies that will come much later in the course, maybe last month or in November, maybe it will come. Okay, so not now, but these are the terminologies that will come at that stage. I just want to introduce them right now so that you cannot define or understand machine learning without, or reinforcement learning without understanding these terminologies. Okay, remember last lecture I gave one example that forget about machine for now. Let's say I am teaching this course, deep learning, right? I am teaching this course, let's say for third time. Now, first time I taught this course, I received some feedback from the students. Based on that, maybe next time when I taught, I made some changes in the way I teach syllabus. Maybe I trimmed a little, I sharpened certain portion of the syllabus that this is what students are finding interesting. Maybe the number of homework I reduced or increased, I don't know, right? And something like that. So this you can think of it as a reinforcement learning. And if I think of it as a reinforcement learning, then this class is the environment. I am the agent. I am teaching, that is the action I am taking. The feedback is the reward. And based on that, I am changing my action. Based on the feedback, I am changing how I teach, what the syllabus is, and all of those things the next time I teach it. Okay. So that is how you can think of reinforcement learning. I mean, that is what reinforcement learning is. And example of reinforcement learning? No, not algorithm. Example. Autonomous driving. Then game. Games are based on those who like to play game. This is how it, the computer game again. This is how it works, right? Scientific example or engineering example, control, planning. Those are again places where reinforcement learning is used. Aircraft control, robot control, vibration control.
So the loop by which we train the deep learning,
Deep
neural
learning?
network, that is also some sort of like this.
Good question. So the question, if I have to frame it in a different manner, can optimization be thought of as a reinforcement learning problem? Or rather, can reinforcement learning be used for training deep learning models? The answer is yes. I mean, that's how large language models are fine tuned. So optimization can also be imagined as a reinforcement learning. In fact, there is a paper 2016 by, or I don't know, remember the name, I'm very bad with names, but it is from UC Berkeley. And the paper title is Learning to Optimize. So that is the first time I think where they showed that you can imagine reinforcement learning be used to learn how to optimize. Okay. So learning to optimize is that paper. So yes, that can also be imagined as a reinforcement learning. That is also a good example of reinforcement learning. But remember, reinforcement learning has a lot of issues also. It does not scale, very slow, and therefore it's only used for fine tuning mostly, not for training from scratch. So those are obviously there. But yes, you can think of optimization as one way of reinforcement learning. I'll even say you can think of generating new samples as a way of reinforcement learning. Where should I generate the next sample so that the information gain is maximized, or in that sense also training sample generation, right? So yes, okay.
Sir,
Hmm.
can you not say GAN is also a
No, in GAN you have data. In GAN, it's not a reinforcement learning. There is a critique. The idea of critique is also there in reinforcement learning. But critique being there does not make anything a reinforcement learning. Is GAN acting and then based on that self-correcting? No, you already have a data to start with. So GAN is a classically unsupervised learning. Okay. So now I will not ask for examples of reinforcement learning because I am expecting not many of you have done a course on reinforcement learning. I mean, I know he has done, so he was saying Q learning, actor critic, and all of those things, but most of you have not done that. So I will not ask for example, but I will rather tell you the examples. There is this idea of deep Q learning. There is this idea of DPO, which is mostly used for large language model fine tuning. There is this idea of PPO, policy optimization actually. Then there is this actor critic algorithm, soft actor critic, and all those variants are there. So these are many, there are many algorithms of many reinforcement learning algorithms that are there. There have been some significant development in that field as well. Okay. But what I like to talk about is type of reinforcement learning. Like there was this classification and regression, like there was this distribution learning and then clustering and the feature learning or feature space, right? So like that, types of reinforcement learning. Reinforcement learning also can be of two types broadly. Types of reinforcement learning. So there is this, I'm guessing most of you might not know, model based and model free are the two types of reinforcement learning. So there is this idea of model based and there is this idea of model free. Okay. What is model based? Model based, so in reinforcement learning there is this idea of states. State means you are at right now, your whatever you are in, that is the current state, and then what will that changes with time. So in model based, the state transition model is known to you. You can predict from ST, if I take this action, what will be ST plus 1. Okay. For example, okay, I'll come to this example later. And in model free, this model is not known to you. So in model based, the state transition model, I mean generally it is transition density, but anyways, state transition model is known. Okay, which means if I take an action and if I know the current state, I can predict what will be the next state, what will I observe. Okay, if I know the current state, and I'll ground it in an example very soon. So for now I'm using this abstract terminology. If I have a current state and if I take an action, I can predict what will happen without performing that action in reality. I have a model that can predict that. Okay. In model free, I do not have that model. So I have to go and actually perform that experiment to know what will happen next. So in model free, no state transition model. So now let me give you two examples. Both will solve using reinforcement learning. And let us try to understand what this transition model might mean, right? So example first, right? Let us take the same example, right? The classroom, right? I'm teaching a course. First time I'm delivering it in certain manner. I'm receiving the feedback, and based on that I'm changing. Do I have a mathematical model that can predict that if I teach in this manner, this is the feedback I'm going to get? I will not have mostly, right? I can fit some model and all of those things, but mostly I don't know the mathematics of that, right? So that means that model is not known to me in this example. That is an example of model free. Okay. Another example. This building is there. There is a controller at the top. There is some earthquake coming, and that earthquake magnitude can be, or the time history can be measured, right? Now, because there is a controller, it will give some force in the opposite direction so that the vibration is minimized. Now, in this case, given that, I know the earthquake motion, and I know I'm giving some control force, can I predict what will be the response? I can use finite element model, for example. I can model it as those who have done a vibration course, I don't think many have, but some of you might have. In that case, I can model a vibration problem. I know the equation is mx double dot plus cx dot plus kx is equal to f, given that it is a linear model, linear system. And there I can always find out that if I give some force xn, and given I know the earthquake motion, what will be the displacement? So the model in this case is known to me. This is, this is a problem that you can solve using model based. Can you solve it using model free also? Obviously you can. You don't use the model. So model based you can always solve using model free. Model free using model based might be tricky. You might have to use some surrogate model, some approximate model, and something like that. Now in this example, two examples, let us also try to understand what is the state, right? In the vibration problem, I'm trying to minimize the, let's say, top floor displacement. So my state variable is top floor displacement. And I know that if I know the top floor displacement now, I can predict the top floor displacement at the next time step given some force. So the state variable in this case is the displacement. Okay. In the model free setting, right, it is difficult to define state variable because you are directly giving a reward. You might not know the state, but let's say if I have to define state variable, hopefully it is an ideal world, state variable can be your state of learning, how much you are learning, and if you are learning mode, you are happy. World does not work like that, but let's assume that is the scenario, then maybe that is my state variable. Okay. So sometime it might not even be possible to define state variable, but we try to define something. It might be that I'm directly getting a reward without going to the state variable. Like in this example, I'm directly going into the reward, right? Feedback. I'm not even getting the state variable. I'm giving an action, and based on the action, I'm directly getting a reward. Or the other option is I'm doing an action. Based on that, I'm getting a state variable, predicting the state variable, and based on the state variable, I'm getting a reward. Both of these are possible. But to wrap things up, model free RL, you do not know the state transition model. You will not be able to predict, or mathematically, what will be how the state will evolve with time. How the state will evolve with time, you will not be able to predict. Okay. In model based, you have that model and you use that model to plan. Because if that model is there, you will not actually do the experiments. You will plan and then perform action in the real world. Any question on this part? Because this was probably some first thing that was new.
So in what paradigm will learning be modeled?
learning the model, mostly it is we frame it as a supervised learning, but you can also solve. So people have solved it also as a RL problem. And there is a framework called Discover where they have framed it as a RL problem. So yeah, mostly one of these two. Yes, you were saying.
Reinforcement learning, do we assume that the next state depends only on the first?
Good question. So I talked about Markov decision process, right? So there is this. Most of the time we work with first order Markovian process. So if you work with first order Markovian process, that's what first order means. But if you're using higher order Markov, then it might depend on the previous states also. So in reinforcement learning, what we do is we have a buffer memory. So we keep the buffer based on the previous history and then also make it function of that. So use first order, but there is a buffer which keeps the history. Okay. And I will say for mechanics that is quite reasonable assumption first order. Why? Because remember the time integration schemes, right? How do you find the time integration scheme? Most of time integration scheme is yt plus 1 is equal to yt plus some term which is function of either yt or yt plus 1 or something in between. So you can see there itself, and this is the numerical methods. It's actually first order. So in mechanics, mostly first order works, but there is this concept of time delayed dynamical system where actually things go higher order. So to answer in RL, no, not always will not assume it is only the previous thing, but we try to model it like that because that makes our life simpler. Okay. Any other question on this part? No? Okay, so then let us do one final thing. Let us try to draw or put all of those, summarize all of those things, all of these things, right? So machine learning, and we said that it can be of three types, right? Supervised learning, unsupervised learning, reinforcement learning. Okay. And then supervised learning, we said it can be classification or regression. Okay. Examples of classification was, for example, logistic regression, and then this is linear regression, let's say. Example of unsupervised learning is, or sorry, not example, types. Clustering, then we said distribution learning, so I'll write DL. DL is deep learning, so maybe I should change it. Yeah, maybe distributed learning. And then the last one is feature extraction. In clustering, the example was K means. In distribution learning, any generative model, but I am going to write mixture of Gaussian. I am writing the short form. If you're interested, you can write the full form. So that don't. So emoji is mixture of Gaussian. Feature extraction, let's say PCA. And reinforcement learning, we said model based and model free. I will not give the example right now. We'll keep it for when we discuss RL at the end. Okay. Okay, but deep Q learning, for example, is model free, just as an example. Okay. So this is how it looks.
So I have two questions actually. एक जैसे हम लोग का रिग्रेशन है जो सुपरवाइज्ड लर्निंग के अंदर है, तो क्या उसमें जितना डेटा हमारे पास पूरा अवेलेबल है उसके बाहर के डेटा को जैसे एक्सट्रपलेट कर देते हैं लोग, क्या वो भी अवेलेबल मतलब वो कर सकते हैं नहीं?
So I think the question is that, and it's a very generic open question in machine learning, which is that can we, how well machine learning extrapolates? He asks mostly in the context of supervised learning, but it can be a generic question, right? Mostly it doesn't. There is a series of work. For example, time series model does extrapolate to a certain degree. We'll see LSTM attention, it does to a certain degree, right? But extrapolation is a very challenging problem. most of the time, for example, can I extrapolate 2 million time steps ahead? Mostly the answer is no. A million time steps it cannot. But can I extrapolate, let's say, 1,000 time steps ahead? Yes, depends. I mean, there are models that can. And then there are some models which can actually extrapolate much longer. For example, neural OD is one such method which can extrapolate quite long. Liquid neural network is one such model which extrapolates quite long. But in general, extrapolation is a difficult problem. Most models are not able to extrapolate. I mean, if in short, that is the answer. Okay. You said you have two questions. What is the other one?
क्वेश्चन इज कि जब भी हम एक्सपेरिमेंट करते हैं हमारे पास डेटा होता है तो उस डेटा को किसी भी मॉडल में यूज करने से पहले जो आपने सुपरवाइज लर्निंग में बताया मोस्ट ऑफ द टाइम हम वही करते हैं फीचर एक्सट्रैक्ट किसी का आरएसएम निकाल रहे हैं कर्टिस निकाल रहे हैं है ना तो क्या ऐसा हो रहा है कि सुपरवाइज्ड यूज करने से पहले somewhat we are using unsupervised learning?
Again, good question, but okay. So what he asked was that often in experimental setup, so he's the experimentalist. So in experiments, when you get data, we sometimes process the data. For example, those who are from mechanics background, when you take data, strain gauge, for example, it gives strains, but from there you process to find out stresses and displacements and all of those things, right? So that's what is done. So this processing, is that feature extraction? No, that is data processing. Feature extraction, that's why I said low dimensional. So that's not what it is. But the second part of the question is even more interesting, that can unsupervised and supervised be combined? The answer to that is yes. Semi-supervised does that. Self-supervised also does that. Both of them does that. They do it in a slightly different way, but both of these algorithms combines this idea of unsupervised and supervised. Unfortunately, none of this will be covered in this course. Neither semi-supervised nor self-supervised. But if some of you want to do it as a project, you are welcome to do that. You can work on self-supervised or semi-supervised. It is allowed to work on projects which is like delta X, away from what is being covered in the syllabus. So self-supervised is a very popular area right now. Semi-supervised right now is not that popular, but it was popular. But both of this combines this idea of unsupervised and supervised together. And why is it necessary to combine this is probably a valid question. The reason is that to get supervised data in reality is very difficult. You do a MRI, right? Now, who will annotate the data and say whether there is a tumor or not? Some doctor. And that doctor or that person is very busy most of the time. And how many data can he annotate or she annotate? Only a limited, right? 100,000 what? But how many MRIs have been performed on a daily or yearly basis? Maybe in millions. I mean, till date, how many MRIs have been performed? I don't even know, millions or something like that, right? So clearly you can see that the number of unsupervised data is always much higher than the number of supervised data. And so the idea is that can you combine these two ideas, that more data from unsupervised and then fine tuning or learning from the, so that is the broader idea, right? But again, I'm not going to details because that's not part of the course. Okay. Any other question?
I heard this term called transfer learning. What is it?
Yes. So transfer learning is mostly supervised. So transfer learning is you train a model. Let's say I train a model to classify between dog and cat. And then I want to use that same model to classify between whether there is a tumor or not tumor. So in that case, I will take the trained model because it has learned binary classification and then fine tune it on the tumor data set and hope. But I will not train everything. I'll fine tune only some of the weights, and that is the idea of transfer learning. Okay. So transfer learning is transfer learning is generally you have data, lot of data, all annotated. You train the model on that, and then in a domain you might not have enough data, you fine tune on that. For example, ImageNet. ImageNet is a very big data available for computer vision. You train your model on ImageNet, and now for tumor you will have what? 500 data is more than enough. I mean, not more than enough. I mean, more than what you can expect to have at a given point of time. Because remember, all this privacy issue and all of those things are also there. I mean, they cannot share all of those things. So now, if you directly try to train the model on only those 500 data, it might not perform that well. But what if I first train a base model on this ImageNet, remove the last part because it was multi-class, and then put a binary classifier there and train this, fine tune it on this one. So this is one example which many people are doing. So that is the idea of transfer learning, but here remember that both are supervised to start with. Okay. Any other question? If not, let me proceed to the last part. Although I might not be able to complete it today, but let me start nonetheless, which is review of linear regression. So what we will do is as follow: we will review linear regression, and from there we will go to logistic regression, which will allow us to go to perceptron. Okay, so that is the flow we will use. So let me start with linear regression. From there, logistic will not happen today definitely, but yeah. So one popular supervised learning algorithm is linear regression. Okay. So linear regression, right? Remember, linear regression is a supervised learning. So my data set will be of this form. Sorry, xi, yi. This is my data, right? And what we are interested in? We are interested in learning a model M that maps from x to y. Okay. You will see that, I mean, I did not tell it, but you have probably noticed that when I'm writing this model, I'm using capital X, capital Y. And when I'm writing data, I'm using small x, small y. So small x means, so capital X are variables. So let's say capital X denotes height. Small x is one height that I measured from one of the student, let's say. Okay, so capital X means the variable. Small x means one sample or one value of that variable. Okay, so that is why I'm using this different notations by design. So this is the objective, right? Now remember that in any model, we start with some model assumption. We assume some model to start with, that this is the model which I think is reasonable enough and should work for my data set, right? And obviously then they have to give some proofs that okay, this is actually good, this can approximate any function and all of those things, but broadly we start with this idea that this is the model, and we will work based on this model. Okay. So in linear regression, this is linear, right? So model is assumed to be of the following form. Okay, and the form is y is equal to A transpose x plus b. Okay, so in linear regression, again, I mean, I will generalize it later, but let's say in linear regression, we assume the model to be of this form. Okay, where x is my variable, a and b are the unknowns. A we call it weight, b we call bias. A, b combiningly are the model parameters theta, y is my output. So in linear regression, we assume it of this form, where A is my weight vector, B is the bias, the other things you know. Okay. Now this is not the generalized linear regression model, but the most basic linear regression model. Okay. From here you get, we also have what is known as the generalized linear regression, and there we write y is equal to A transpose phi x. Okay. You will see that the B is now not there because I have absorbed A into B, sorry, B into A. What is the difference you see between these two things? X has become phi x. That's the only difference. What is phi x? Basis. Phi x is your basis vector. Potentially some non-linear basis vector. What was the limitation of the first model? It was only linear, right? So it can only draw a straight line in some hyperplane. The second one, phi x is non-linear. Phi x can be x, x square, x cube, anything can be there, right? Sin x, cos x, some complex function and all of those things. So that's why, so it's generalized, but it's still linear regression. Although there is non-linearity there, it's still linear regression. Why? It is linear in the parameter space. So linear regression is called linear regression not because it fits a linear function. Linear regression is called linear regression because it is linear in the parameters, not in the input variables. So that is something, that distinction is something you should be careful about. I mean, I have often seen that linear regression, people think that it's a linear fit. It's not a linear fit. It can be highly nonlinear also. The only thing is that the parameters are linear. In terms of parameter, it's a linear function. Okay. So linear regression is called linear because it's linear in parameter. It's linear in terms of the parameters, which is A in our case. We will make it W or theta later, but for now I'm using A. Okay. That is why it is called a linear regression and not a non-linear regression, for example. Okay. Now, to use this model, can you use this model? Or do we need something to use this model? We need to find A and B, or we need to estimate A to use this model. I mean, can I use this model to make prediction? I cannot. I do not know what is A. I know A is a vector. That's fine. But what is the value of that vector? I do not know. So I need to find out the value of the vector A, right? If I know the value of the vector A, then this model is ready to predict for a new x. For a new x star, you can see phi of x star will give me, I mean, phi of x star is known to me because x star is known to me. And if A is known to me, I will just multiply those and do the summation, and that will give me my y star, right? So to use this model in practice, we need to find A star A. How will you find A? To find A, we need to define some metric. So we define what is known as loss function. Okay. So to that end, we define a loss function. And loss function, what is a loss function? It is, I can formally define it, but basically you can think of it that if the loss function goes to 0, that means it's the best thing and it's a positive quantity. It cannot be negative. And it basically maps it basically maps your output, right, to a scalar, which when minimized means you are getting a better model, and it is always greater than equal to 0. There is a formal definition. I'm not going to the formal definition, at least not now, not today. But that's what a loss function is, and you can define your own loss function, by the way. Define a loss function, right? Example of loss function is, for example, the most popular one is mean square, right, which is 1 by n summation over I yi minus A transpose phi xi square. Okay. Now, in some books you will find that instead of 1 by n, 1 by 2n is written. Both are correct. That number 2 comes from basically when you take derivative, that 2 and 2 will cancel out, so that's why they keep that 1 by 2. Okay, and also that comes from Gaussian distribution likelihood, but I will not go in there. So this is one example. I will give one more example and then we will stop and we will start from here next time. L is equal to 1 by n summation over I A transpose phi xi. Okay.
Should it be small y or capital Y?
Which one?
So
This one?
yes.
Small, because I am finding it for each data point, right, and then doing the summation. So that's why. Okay. And then obviously with this we do minimization to find out which, again, we'll next lecture I will start from here only. Next lecture I will start from linear regression only. So we'll repeat this part on Thursday and then proceed and complete this review. Obviously I could not complete the review today, but that's fine. Okay. Thank you. Yeah.
Shouldn't we add a bias terms in the A transpose phi?
Oh, I did not, because I'll tell you why. Maybe next class. So what I did was inside phi there is phi 0 also, which is 1.
Sir, I did think of that, but does that not reduce the kind of expressivity, because then your P is constrained to the summation of A's parameters?
No. It's the same expression. So for example, suppose my equation is a0 plus a1x. Their bias is there. I can always write a0 a1 1x. So instead of only, otherwise I was writing what, a0 plus a1 x. Now I am saying a is having a0 and a1 and then x is having 1 and x. So it's the exact same equation, and I will show it next time, but if you do it and write it, you will get it. They are exactly the same. The thing is that whether you are counting 0 to k or 1 to k and adding one thing, that's the only thing. Okay. So I will do it, show it next time. Okay. And if you want it now, then we have to go outside and then, okay, because right now the next lecture will start, so I'll stop. Okay. Thank you.